I'm only talk like into the void, into my laptop. Because over the last 3 years in Corona, you mainly did like virtual presentations, and then you drop out and you say end meeting now for all. So I'm really looking forward to the Q&A session and also for the networking afterwards for all the people who are here and for the people who are like virtually in the call. Yeah, come to Berlin. It's an amazing city. It's really lovely, and maybe you can make it to the next meetup. So today I'm talking about incorporating new knowledge into. You have to confirm it somewhere. So I'm talking about how to incorporate new knowledge into language models. So why is it relevant for us? So I'm working as director of machine learning at Cohere AI. And what we do is we train a model to really large sizes, to 100 billions of parameters, to provide them as an API for everyone. So it's not easy, it's not cheap to train these massive language models with 100 billions of parameters. So we specialize in the knowledge how to train them, how to expose them, but often they become stale. So you ask like, okay, can you write like some article about the current US president, and then the model creates like an article about Barack Obama. You're like totally disappointed. So how did you miss that there was like some Donald Trump and now Joe Biden going on? And so it's a really relevant topic besides others. So first we train these models, we check out, or we do research how you can adapt them to your data set. It's really easy to use for them. It's a pay-as-you-go API, and it's optimized for speed. And we're also hiring. So if you want to learn more about how to train massively large language models and how to create like valuable products out of them, feel free to approach me or to apply. So we're looking desperately for great talent. And I know in Berlin, there's a lot of great talent. So I'm specifically working on two directions. One is text classification and neural search. Today, I will talk about neural search, presenting some research from my PhD student working on this topic. So you can find a lot more information in our publications and also a lot of open source code. So my particular topic is neural search, and neural search is like really big type. So DeepSet is also really keen on like neural search or search in general. ML6 also has really cool use cases on search. And if you follow the space, there's like a lot of hype. And the first question is like, the hype justified or not? And I would say, yes, it's justified. So I present like a really simple example, real example. So here as a data set, we have the simple Wikipedia, simple English Wikipedia, 170,000 documents. You have a really simple question as a user, what's the capital of the United States? And then you use the tool everyone used for the past 20 years, which is Elasticsearch using lexical search in BM25. You run this query and you get amazing results about capital punishment in the United States. So it has capital in it and United States. And so BM25 thinks, yeah, capital in United States, that's good. Yeah, maybe first hit is bad, so maybe second hit is better, which talks about Ohio because it's a state in the United States and it also has capital. So maybe on the third try, so third hit is about Nevada. It's also a state in the United States, so it has capital. So from a lexical overlap, it looks like really good hits, and that's what you get from Elasticsearch, lexical search, BM25, Lucene, Solar, whatever you use. I go here. But as a user, you're not happy with that. And if you instead go from lexical search to neural search, you hit the same query. It's like a really simple model. The first hit you get is like Washington, D.C. is the capital of the United States. Your user is happy, it's a perfect answer. The model is even smart enough to think about like, okay, sometimes users are stupid and they do typos. So instead of like searching for what's the capital of the United States, they may want to know what's the capital of the United States. So maybe I also present a result on like the United States capital. So just in case the user misspelled the word. So how does neural search work? There are like many, many different approaches. I'm only able to cover one approach, which is most commonly used in industry, which are using bioencoders. So bioencoders work on vector spaces. So that's math you learned probably in 11th grade, where you maybe thought, okay, it's not relevant. But if you go into neural research, it's all about vector spaces, and they are amazing. And I hope I can share the enthusiasm about vector spaces with you. So you take all the Wikipedia articles, you put them in a vector space, and then you have some way to encode the query, what's the capital of the United States. You also put it in the vector space, and then you check what are the closest documents here in the vector space, and these are the relevant documents, hopefully, for your search question. So that's a really simplification of the search problem. And how do you do that? So transformers to the rescue, you use some transformer architecture like BERT. You process independently the query and the document. So that's also why it's called bi-encoder. You have like two encoders. Even such in most cases, it's the same encoder. You pass the document or the query independently through the transformer network. You get contextualized word embeddings as an output where you run some pooling operation. For example, you take the mean of all contextualized word embeddings. This gives you some fixed vector. So here's like a 2D vector, and then you can run cosine similarity to get the similarity between the query and the document. And this allows you to do search in a really simplified way. So today I want to talk about like how can we bake a new knowledge into models. And there's like a nasty thing with our world, it's changing. So things are happening and language develops. And if you ask BERT, who's the current US president, it still thinks Barack Obama is the current US president. So it has never heard anything about Donald Trump or Joe Biden. So if you ask any questions about the US president, everything is pointed to Barack Obama. Also, if you ask like a state-of-the-art open source model for neural search, like how is COVID-19 transmitted, and you have like 4 documents which you want to re-rank, the model thinks the top of it is about Ebola is transmitted by a direct contact with blood. And only on the 3rd place, so 3rd out of 4 documents we search, corona is transmitted via the air, because BERT was like trained in a really innocent world where COVID and corona was completely unknown. Corona was only mapped to the beer name, so it has like no idea that COVID and corona is the same. But if you use it today, this would be kind of bad to have such a model which lacked all the knowledge about everything what happened since 2017 when BERT was trained on the data stamp of the BERT model. So a big question with these bioencoders is how do they handle unknown words? So unknown words can be words that it has not seen during fine-tuning or it has not seen during pre-training. So the BERT network has never seen about anything about COVID-19 and SARS-CoV-2. And there's like a lot of things that are happening. So for example, there's like XLNet, some transformer architecture. So every week, another transformer architecture is announced. Flex exchange is some cryptocurrency. So every day a new cryptocurrency is announced. Forward is not a spelling mistake. It's a startup from Israel. So every day, thousands of companies are created with really creative names. And you have something like this OXC004. And if you have never seen this, it's like impossible. So if I would ask you, so maybe a guess, what could this be? Like this hexadecimal code, what does the meaning of that? Any educated guess in the back? No, it's an error code you get with the Windows activation. So if Windows cannot verify your activation, it says, okay, we have arrows C0, blah, 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 blah. And then you can Google for it, and then you can find ways how you can solve the error in Windows. So it's really hard for these models to know what is coronavirus, how is it connected to COVID-19, to SARS-CoV-2, if it has never seen this in any text, in any pre-training or fine-tuning. And yeah, so how they handle it, it's kind of bad. So you have some words, so Big Bird Pegasus, that's another transformer architecture from Google for long documents. And you have this document about a long document transformer architecture. You put it in a vector space. And then the question is like, where do you put this in the vector space? So what's the right position in this vector space to put it? And if you ask the model, it thinks, okay, the closest, most similar words is big boss, big data, and big ass. Because it has never seen this word, it has absolutely no idea what it is. And in search, it's really bad because if you search for this document, you might find some documents talking about big ass. Or similar, you search for big data and you find some document about Big Bird Pegasus, which has absolutely no connection. So in 21, last year, we wanted to test this a bit more further, a bit more systematically. So we created with my PhD student, Nandan Thakur, a great person, the peer benchmarking IR, where we said, okay, let's collect a lot of different data sets from a lot of different domains and see how models perform. And out of domain performance, with really interesting use cases. For example, tweet retrieval. We have some news article given and we want to find tweets talking about this news event. So it's not only like I put in like a question, like what's the capital of the US, but it can also be I put in like a news event. I want to find tweets talking about this news event. And we tested lexical search, dense neural search, and yeah, so that's what was the first test we did, besides a lot of others. People before said, okay, these neural search with bioencoders and vector spaces, they're so great because the performance against lexical search is really big. So you get like an 18-point NDCG at 10 improvement. It's like you see it directly as a user. That the performance is much, much better. However, if you go out of domain, if you don't train it and test it on your domain, but you apply these models, for example, on BioArc, which is a biomedical domain, you see the performance drop significantly because the model has never seen all these biomedical terms. And then as I've shown with BigBird Pegasus, it confuses these words and creates like really strange results. And in fact, lexical search was better on 10 out of 18 data sets. So yeah, there's hype, but it's also kind of fragile how they work. So it's not like, okay, you use neural search and everything gets better. It's kind of hard to use them. There are ways to make it better. So the question is, how can we adapt bioencoders or in general neural models to new domains, for example, to a biomedical domain, to legal domain, to, I don't know, transformer, plug-and-place transformer architectures with all these weird transformer architecture names. What you can find previously is called adaptive retraining. So you take some documents from your, like the target domain you're interested in, for example, COVID-19 literature, and then you do retraining on this, like running mass language modeling on that. However, then you still need to fine tune on labeled data you have. So for example, on MS Marco to get a search module. And this step is kind of expensive. So we train our model on like more than 2 billion training pairs. So that's like terabyte of data. So it's like really unscalable. If you say, I want to search in my, I don't know, my diary about Pokemon, it would be really bad to run first pre-training on your specific corpus and then train again on like the 2 billion training pairs we have. So instead, what we want is like the opposite. We want to train once on the data set we have and then have some way to adapt it to your specific use case, to your specific domain. And there, another PhD student, Keishing, invented GPL, generated pseudo-labeling, which is able to achieve this. And the idea is to combine different techniques, different architectures together to get a really nice output. So it works in 3 stages: first query generation, then negative mining, and then pseudo-labeling, which I will go into a bit more into detail now. So you take the document, you take, in this case, a T5 encoder-decoder architecture, and you ask the T5 model, what are good search queries people could ask? So you have some document about Python, and then the model says, okay, yeah, maybe someone asked about what is Python, how good is the readability of Python code, which programming languages use this indentation. So it tries to predict what can people ask about this passage. Then you take this passage and you run it through your corpus to find similar documents. We call it negative, hard negatives. So you ask which programming language uses indentation, and then you find some documents, for example, Java is a class-based programming language, was used one of the fastest programming languages available. And then you use cross-encoder. So cross-encoder, so in a bioencoder, you encode the query and the document individually. In a cross-encoder, you concatenate the 2 texts, like the query and the documents together. And then you have like the powerful, but really expensive, computationally expensive cross-attention between all the query tokens and all the document tokens. And it can give you then at the end, predict some score, how relevant is the document. So for query 1 and document 1, you get maybe a score of 5.2. And for query 3 and document 3, for example, minus 3.8. And if you train then the bioencoder on these pairs, the query document pairs, so the query is generated, the document is the document you have, and some score from this powerful cross-encoder, you train a bioencoder on this, you get a really nice performance in search. So out of the box performance like 42. If you run pre-training with math language modeling, you get like 1 point improvement. So it's a little bit better to search. If you switch to TSDE, which is another approach for pre-training, you get some more improvement. But with generative pseudo labeling, you get much more improvement. And what's nice is that the quality improvement scales with the compute you put in. So you start here with the blue line, so that's the out-of-the-box model, and then you start to train, and you see continually it improves. So you can just let it run for how much time and money you have in terms of compute, and it starts to increase and getting better and better as a model. And yeah, so if you do not know what's in the CGI 10, and you do not know if it's relevant or not, so just to put a real example, so if we take this original document, we do this step for some COVID-19 literature, and then we ask the same question again, how is COVID-19 transmitted? It has learned that COVID-19 and corona is similar, has similar meaning, or is a synonym, and puts the corona transmitted via the air as the correct hit on the first place. So there are still many unsolved issues in knowledge updates. One of the biggest issue I think is like data efficiency. So humans, they're really, really amazing in terms of like data efficiency. So you wake up in November, I don't know when the election was, and you read Joe Biden as the new US president. It's amazing what happens in your brain. So first you update, yes, president. Yeah, that's easy, that's obvious. But you also update, okay, who's the first lady or who's going to be the first lady? So this also changes. You also update which party is in the White House. You also update number of presidents that served hopefully only one term. So, and a lot more things update, like, I don't know, which universities had like the most alumni becoming president and so on and so on. So just from these, I don't know, 6 words, there are like so many updates you can do and you instantly do in your brain, which is totally fascinating in terms of data efficiency. If you take current methods like be it adaptive pre-training or GPL, you require a lot of data. So you need thousands, millions of text to update who is the new US president. So if you want to update word that Barack Obama is no longer the US president, you need to find a lot of documents on Joe Biden, which is doable because it's like really prominent figure. But there's like a large time delay, and also for a lot of topics, there's like not millions of documents. So if you're here in Berlin, there's like some really cool AI startup with a really creative name. So there's maybe one website talking about you. So how can you bring this knowledge about your amazing creative name into like some transformer architectures to know, okay, this is an AI startup from Berlin. So an ongoing research I started earlier this year was to take some tricks from word embeddings. So if you're a bit longer in the field, so in 2013, these word embeddings manipulations were like really interesting and the shit. So you take some word embeddings like man, woman, king, and queen, and if you multiply and subtract and add them, so when you say the word embedding king minus man plus woman equals the word embedding for queen. So a research question I posed is like, can we train the word piece embeddings to allow vector space operations? And we got some interesting results. So this is like only like prototype state. So if you ask a model, what is the best transformer model for audio processing? Again, it's based on BERT, has no idea about transformers, has no idea what is Roberta, deBerta, wave to vec, and VIT. And then, so this is a text embedding model, text transformer model, an image or vision transformer model, and the only audio transformer model is wave to vec, but it has like no idea that wave to vec 2 is connected to transformers and audio, and just put it on like the 3rd place out of 4 possible documents. Now we can do the word piece operations. So we say VIT, that's transformer plus vision, wave to vec 2 is transformer plus audio, and Roborator and pBERT and BERT is transformer plus text. So it's just like these updates, these operations, really simple. You take 2 vectors, you add them together, and you ask the same question again, and the model have instantaneously learned, okay, wave to vec is the best answer to this question. So in a prototype stage, it looks really cool. we found that it's really hard. The next stage is like really hard, like which words should we update? So if you give us a bunch of documents, I don't know, on your use case, which words have like a different meaning than to what the model has learned? So also, how do you define the update automatically and how do you evaluate this? So here in this case, it's easy from domain knowledge. We know, okay, these terms are really important. The network doesn't know it. We can define, okay, bird is a transformer for text. So that's really easy, but how can you automate this? If I give you 100,000 documents, which words are new and have a different meaning and are relevant for this term? So in conclusion, stale models are a major issue, and in all scenarios where up-to-date knowledge is a big challenge. And in search, up-to-date knowledge is really a big challenge because usually you search for current events, so what happened now or what happened yesterday. Adaptive pre-training and generative pseudo-labeling, they can help when you have a lot of data, but they require just too many text evidences for new or changed terms, so they're not able to learn from a single example, but you need more like thousands, tens of thousands of examples. And so there's like really massive time delay until you accumulated a lot of evidence on this new term. And yeah, it's a big research question, also business opportunity. How can we update models from a single text? If you crack this down, it will be amazing and would help a lot of people. I don't know how to do it. So if you ask me, how can we do it? I don't know. It's ongoing research. And yeah, thanks so much for listening.
Yeah, thank you, Nils, for the talk. Now we have time for questions, and also for the people online. Please post the questions in the chat, and we have moderators for the online participants who can then read out the questions. And yeah, also in the audience, of course, if you have questions, we have a microphone there going around. I saw one question already from the online participants. It's about domain-specific vocabulary. What if you have later on a new word like COVID-19, as you showed it? How does the domain adaptation later on then work? Can you extend the vocabulary and how can you do it?
Yes, so if you have domain-specific knowledge, I'd say COVID-19 as a new term, you can add it to a tokenizer. I think the benefit you get from adding it to a tokenizer, so maybe before it was like 2 word pieces like COVID and 19, now it's a single word piece, COVID-19, it's kind of limited. And what's more helpful is to do training on it, like mass language modeling or adaptive pre-training. But as mentioned here, you need a lot of examples. So you need thousands, tens of thousands documents talking about COVID-19 until the model is able to learn what is COVID-19.
So I have 2 questions actually. First of all, thank you for your great talk. So can you explain where in the process of this generative pseudo labeling does actually the new word come into play? Like, I still didn't get how it is integrated into the model.
So the step comes mainly from generating data. So you synthetically generate training data for your domain. So let's say you have some article about COVID-19 as a new disease discovered in China and so on. Then it generates like questions like what's COVID-19 and so on. And some articles, they talk about COVID-19, some articles talk about coronavirus. And then the model learns, okay, there's like some articles, I don't know, this article, coronavirus is a new virus discovered in China, and the other article says COVID-19 is a new virus discovered in China. And then the model asks, okay, which virus was newly discovered in China? And there it learns, okay, COVID-19 and corona must be close because it has the same question. And then the answer is the same. So it learns like from these generated questions, what are like the correlations between different terms.
Oh, thanks. The second question is, how do you deal with the model forgetting its prior knowledge?
Yeah, that's an unsolved problem. So it's not easy to field. So if you update it to a specific thing, so if you bake into and say, okay, now I want to know the model that Joe Biden is the current US president, the model can learn this, but the model is not smart enough to know, okay, I need to update and Barack Obama becomes like the former president. And then it kind of forgets that Barack Obama used to be a president. And it's one of the big challenges, unsolved challenges. People, industry waste a lot of money on this because they retrain the models from scratch over and over and over again, like every night. Amazon Alexa, for example, in Berlin runs like a lot of training things just on new data because they have like no idea how to bake in new knowledge without forgetting previous knowledge.
We have some questions online. I'll read one out. You mentioned about mining negatives. Any idea on how the model can learn about positives to get new correct knowledge?
Cool. So the positives are generated by this query, by this encoder-decoder architecture. So we take this document, ask what are good questions, and then we treat these as positives. And then we just use the mining step to get the negatives.
Another question from the online community. Do you freeze some of the lower layers during fine-tuning?
Yeah, it was a research paper. We did not freeze like any layers because not freezing any layers gives you the best performance, and that's what's relevant in a research paper. In other settings, if you say you do not, I don't know, you optimize for serving a lot of models, thousands of models, you probably want to freeze some layers so that you can reuse them between models and runs, and then just update like specific set of parameters. But yeah, for research, you always update everything because that's the best performance you can get.
More questions. I see a question there.
Hi, yeah, thanks for the talk. Just for maybe a basic question for you, but for somebody that wants to try to train a search model, a language model using these cross embeddings that you mentioned that they were trained based on the score between documents and queries. Where did you get those scores? Where do you get those scores from? Do you have to hand label those? Or they come from that query generation process in T5? Where do those come from?
Yeah, so that's why it's called pseudo-labeling. So pseudo-labeling means you do not annotate it by hand. You could annotate it by hand, but that's cumbersome, what you don't want to do. So what we do is we take a cross-encoder. So cross-encoder is a model that looks at the query and looks at the document and then estimates a relevancy. So it goes like from, I don't know, -10 to 10, how relevant is the pair? And then you train the search model, the spy encoder model, to mimic the scores predicted by the cross-encoder.
So we are running a bit out of time. I will take 2 more questions now and maybe 1 more question from the online community. And then later on, we also have time, right? So after the 2 talks, Nils is still here. I think he will be answering all your questions. Okay, so 1 more.
Thanks for the talk, first of all. And how could we adopt the GPL technique for symmetric search? Basically, when your document is fragmented words or like the words constitute to a sentence which do not have context. So it's hard to generate questions from T5. And also the second question would be, do we need to evaluate the questions which are generated? Are they making any context towards the document before doing training?
Yeah, so that's great intro into like another talk. So BERT models, they are just limited to like 512 word pieces. These are like roughly 300 words, but like every document you have is like longer, and then you start to chunk it down. So you take like your 100-page annual report from Volkswagen, and you chunk it down into like small 100-word chunks where you lose like context. And then you have like issues that you have like a generator which just sees like this text in between and misses completely the context, and then creates like bad queries because it doesn't know what's the context. So I don't know, and maybe it just sees like a single number and it doesn't know, okay, this is the number, I don't know, the revenue some company made last year. Yeah, people working on it to make transformers applicable to longer documents so that you don't have the size limit of like 512 word pieces. Ongoing research, a lot of activity, no great solution yet, but yeah, maybe someone cracks it at some point and develops like a really nice model where you can feed in like arbitrarily long text.
I'll read out one more from the online community. In the GPL schema, without manual tagging of new words for domain adaptation and initializing new vocabulary for the model, like in the case of pre-training, how does the model learn new words? How does it differ from pre-training?
So yeah, as mentioned, so you do not need to add new tokens. That's not really necessary, like for all the techniques. The benefit from doing that is kind of limited. And you not only have like the knowledge of the tokens in the token embeddings, but you also have the knowledge in all the transformer layers, like all the attention layers and so on. So it learns like from the word pieces, what does COVID mean and how is it connected to coronavirus? And yes, as mentioned here, it creates these pairs between documents and queries. And the T5 models does not copy like all the words. So here's like, for example, some information missing. So for example, what is Python? And then the model learns, maybe the model does not know what is Python. So it just thinks Python is a snake because Python was completely new invented. So it learns that Python is kind of connected to a programming language, emphasizes code readability and uses significant intonation. So it learns to connect Python to intonation, even such that you do not explicitly say, okay, Python and intonation or programming language is connected. So the model picks it up from these pairs.
Okay, so Nils said he will also answer some more questions in the chat, right? So he will go through the questions there. Yeah, let's thank our speaker again. Thank you.
All right. Maybe let's turn on the camera. Yes, thank you for the introduction. Also for me, the first time to speaking on the microphone. So weird feeling, but yeah, we will make it. So welcome to my talk where my job set, building a domain-specific search engine. Maybe just allow me to say some words about myself. So I am a machine learning engineer at ML6, and we are consulting the building end-to-end solution, end-to-end machine learning solution, and just try to help to our customer to make some value based on the data they have. We are originally based in Belgium, but as well we first out, and now we have offices in Germany as well as Netherlands. So that's also mainly the reason why we are here. So we have an office here in the AI campus. And one great thing to work at ML6 is that we spend around 15% of our working time to research. It is not really research like research I do. We just try to understand the research and apply it to practical applications. We are internally structured in different chapters. So one of the chapters is NLP. So again, the reason why I'm here, I am part of the NLP chapter and try to, build practical stuff of recent research in NLP. All right, we're working together with a lot of customers that have a lot of information, and we try to make this information searchable, and that's mainly the reason why we build such search engines. The documents are usually in a lot of formats, structured data as well as unstructured, like PDFs, images, a lot of metadata, logs. And we also deal with a lot of domain-specific data sets. Some slides to just recap the last talk where we start. So nearly every search engine is a keyword search engine. So we just searching for words. For example, if we try to search which wild animals live in Africa, we get documents that containing words Africa wild animals, and just base the count of the matching words. But it's not state of the art anymore. And as we learned some minutes ago, the new state of the art is semantic search. So, and now we are really able to use recent transform models to embed our documents and queries into the embedding space, calculate closest distances, and retrieve documents based on the vector distances. That is just one part of the whole search architecture. So we are just talking about this part here, mainly the finds a concrete document. But there's also other stuff in the whole architecture that still needs to carry it on. So usually we start with data ingestion, add some transformation steps, for example, data cleaning or splitting up the documents into smaller pieces just to overcome the issue that the question some minutes ago was. Add stuff like pseudonymization just to remove private information, for example. And then we transform the document into the embedding space by using recent machine learning models stored in a data store. And during query time, we do the same for the query. So basically just embed the query as well. And try to get closed documents by using the embedded query and the embedded documents. Return possible candidates, and then we can apply different approaches like do a re-ranking to get the most relevance, or do key phrase extraction, or even QA models. So in the example here, we can really answer the question, which what animals live in Africa, by getting back to documents, apply different techniques, and get, let's see, the list like lion, zebra, Africa, wild dog. Just to show one use case that we implemented some months ago, we did implement a search engine for the Federation of Notaries. That's an organization in Belgium that mainly archives a lot of legal texts, so that notaries are able to search information, sample use cases, and just find fast the correct information. And we basically built a whole pipeline by setting up the ingestion, remove secret or personal information, and at the end provide a front that the notaries are able to find concrete solutions. The question now is how you can do it as well. So let's find some things in Haystack, and probably a lot of people find it funny, since I guess a lot of people are working for DeepSet here, and I just want to point out to this nice framework. I do not want to have any credits for this, since it's really open source. I get no paid for that. It's a great framework. You can easily build your whole Google search system just by applying, or just write a few lines of code. Really just need 1 hour or so. Mainly including tools for NLP for search, latest language models, also scalability features. And the greatest thing that we discovered recently is generative pseudo labeling. So maybe somebody had heard about it already. Just kidding. And thanks to awesome contributor, we are now able just to use it inside of the framework. And what I actually mean with, let's just use it, I'm going to show now. So let's put everything together. So you can really do it in a few lines of code. So first of all, you have to create your document store by just define it. And also you have to define the retrieval model that will do the embeddings. Then you have to just write the documents to the document store, and you're ready to go. And you have the document store with the embedded documents. And afterwards, the only thing you have to do additionally is just to initialize all the 3 parts that are needed to apply GPL. So you need a question generator. You can do it with this line. We use here a German T5 model to generate the queries, just because we're working a lot of German and Dutch-based data sets. And as well as pseudo label generator. The crossing code is already inside the pseudo label generator class, so you do not have to carry about that. And that's it. Then you can really run the training, and at the end you have a retrieval model that is already adapted to your domain-specific data set. To make it complete, you need still 3 more lines of code. By just updating the embeddings in your data store, and then you can build a pipeline where you can really just put your query in and run it. As I mentioned, we are located in Belgium and also Germany, so we are working a lot with Dutch-based data sets and German data sets, so mainly non-English data set. And we think about what we can do to apply the technique also to non-English data sets, just to try it out and can bring value to our customers. So, and just pointed out that everything you need to apply to non-English data sets is there as well. So the bioencoder are existing, also frequent multilingual ones, cross encoders, cross generators as well. And you have also already different data set like the MS Macro data set that was already translated that you can use to train new models for the GPL approach. We ended up by building a little demo just to showcase what is even possible to have a semantic search. And we just tried to find a public domain-specific dataset that we can use to show it here. First thought was we are going to use plenary discussions, but it worked not well. So we called the Bundestag and just looked for topics inside of the plenary discussion. And the main issue was that during one day, different topics are mixed together. So we had to do manual clustering and it was a lot of work. So we skipped it mainly. The second idea was to use manual products. For example, you can Google for car manuals and just have a document and contains a lot of technical words that describe how your car works. Also available in different languages, but yeah, we have to deal with PDFs. And yeah, if you want ever try to transform a PDF to plain text, it's not a funny thing. You have to do and a lot of edge cases. So we skipped this as well. But we ended with a nice data set. We choose the election program of the last German election. We just looked out for parts that we can use. We use CDU for that, just because of the alphabetical order, and skip the first one for some reasons. And to have also that data set, we use just a political news data set that we also found as well on GitHub. All right, I would say it's time for the little demo, and we can see what semantic search is able to do. By the way, the space is also available on GitHub, on Hugging Face, GitHub as well. GitHub contains all the code that is needed to build it, but we also publish the application itself on Hugging Face space. You can feel free to just enter your search query and play around with that. So I just prepared some examples. So if we, for example, searching for tempo limit, we will see that we get some results. Let me move this away. We've seen the term frequency burst document frequencies, basically lexical search. We see really the values that occurs here, right? We have the word tempo limit, so that's the reason why we will have the document here. But as well, semantic search find also stuff that contains a tempo based on the similarity score. But if we now are searching for examples that containing words that are not in the documents, we can really find the semantic meaning of the documents. For example, if you want to know one with words legal, you will probably find nothing with the most frequent words. That would be just because it not contains the word itself, we get really messy result. Also, semantic search was not really able to find a great result because semantic was not learned. But if we go to it's a good example for a live thing, it's not working. Usually you find here example where it say we are not for cannabis legalization. Why it not match here? I have no clue, but I forgot the last word. I see. Thanks. Let's check it again. Okay, I hope that's a word late. Anyway, if anybody figure out what is a query and one would was legal and you are able to find that the CDU want not to legalize cannabis, feel free to send me the query. Yeah. Yeah, that's it mainly from our side. If you have any questions, feel free to ask. And again, just feel free to use Haystack to play around with that and just train your domain specific search engine for your data set. Thank you.
Yeah, thank you, Matthias. And maybe there are already some questions here in the audience, or maybe online. We have more time to think about questions. I didn't see anyone.
There's one.
Yeah,
I mean, it's a question for Haystack, I guess. Like, what is the, I mean, is it based on an AI algorithm or like is it an exhaustive search which is happening beneath?
Sorry, could you repeat the question? So you're asking for?
So I want to know, like, is exhaustive search is possible on Haystack or is it based on some AI algorithm?
No, it's really Haystack. So we used Haystack here just to set up a new search engine here in the Hugging Face space, and we just use complete Haystack tools. So mainly a document search, it's really just in memory here for the example, but you can also connect different database like Elasticsearch to your Haystack framework. So yeah.
Thank you.
more questions. Okay, yeah, there.
Hi, thank you for the great talk. I have a question that have you compared the semantic search with hybrid of vector and BM25?
Not now. Also mainly for the reason it's hard to find or to create the data sets that we can use for evaluation. We know the results from the paper of the Nils Research Group, but we also tried out to create the data sets that we can use to evaluate German or Dutch search behaviors. But yes, it's an ongoing process. We have some data sets internally, but yeah, we are not allowed to share, obviously, since customer related data. But yeah, so actually we try to build the kind of data sets we can use related to yeah, non-English based yeah, languages.
Hi. So what is it inferencing? Like, where do you get this result from? Is it like a vector embedding database somewhere, or?
Yeah. So it's mainly the semantic search part in the domain, and that semantic search are really the vector closest distances. So similarity score is the cosinus similarity between your query and your documents embedded in the vector space.
Where is it stored? Or do you have to store? Is it a model?
It's stored in just a memory. So we actually model the transform model to embed the vectors in the words into vectors and store the vectors in memory here.
Now the online community.
Did you perform an analysis of how neural models work compared to knowledge graph QA for your use case?
Knowledge graph QA? No, not now. Also not sure how we could apply knowledge graph QA. Do we mean by analyze different political statements and build a knowledge graph?
I could imagine maybe there are some structured knowledge bases around that kind of data sets.
Yeah, not really. I mean, it's a plain election program, right? You have just, yeah, that's stuff that you can read if you go to an election and just vote for a party. Yeah, you should read beforehand just to be sure what you're voting.
Yes, thanks. I want to ask how expensive is this GPL fine-tuning? How much compute do you need to invest?
Good question. The training for this example here run, I guess, for 4 hours on, yeah, I guess a P100 GPU. So I have no, not in my mind how much it costs, honestly, but I guess, yeah, some euros, maybe 10 euros if you run it for 4 hours.
So I was wondering how well the approach scales to larger data sets.
Also good question. Honestly, we did not test it yet. Since the constant is quite new. Also, the release of Haystack just happened, I guess, 4 months ago. So we plan to use it also in client project maybe. So just we try to test it, how good it performs. And honestly, it's also just a small data set. It's a PDF, or not the original was a PDF containing maybe 100 pages. So unfortunately, I cannot answer this yet.
Thanks.
Okay, I see one more question in the back, and then maybe we can already conclude this Q&A and start with the discussion here in the breakout rooms online.
I was just wondering, this looks super cool and I want to try it out. Is it quite sensitive to the choice of like base language model and things like that? Or are you pretty safe just doing something pretty generic?
Also good question. I would say just try it out. I mean, just go to Haystack, use it, implement. I mean, the code is also there. What you can do is basically change the language model as well and try how it looks like if you apply it with a different language model. Yeah.
All right, then thanks again to Matthias